Hi everyone, today I'm going to present about hardware-software partitioning for embedded systems using hybrid algorithm, genetic algorithm, particle swamp optimization in a 3 levels. My name is Surendra and my partner name is Mustamin. To give a background, what is a hardware and what is a software, and what is this hardware-software partitioning? In a hardware-software partitioning, there would be a SoC, system on chip, and the entire system can be developed entirely in hardware or entirely in software. What would be the limitation? If I do everything in hardware, the total cost will increase a lot because hardware is very expensive. If I do everything in software, it would be very slow. Even though I save a lot of cost, it would be slower response time. Using optimization techniques, we can achieve with a low cost, with a better timing. So that is our objective, to achieve less cost and faster time response. To do that, we have to find a mutual agreement between hardware and software portions, what to be implemented in hardware, what to be implemented in software. Manually, if you do, there would be a lot of errors and it would take a lot of time also to decide. Instead, if you use optimization techniques, something like genetic algorithm or a particle swamp optimization, they can give automatically just a software. It will run very fast and it gives us the optimal solution. Yeah, so that is the proposal. What is a hardware? Hardware is a parallel circuit which can do a lot of operations at any given time parallelly. Example, ASIC and FPGA. Field programmable gate array. This one is a integrated circuits, asynchronous and synchronous. The hardware is a high cost, however it can give you a faster result, and parallelly it can do a lot of operations at the same time. Software, it has a limitation. It cannot do so many operations at once. It will do one by one. The software means microprocessor, something like an Intel processor. It is a sequential. It is a low cost compared to FPGA and ASIC, and it is slower compared to FPGA. If you take a SoC, system on chip, it will have some hardware portion and most of the software portion, meaning there would be some FPGA kind of blocks or a space, and there would be a microprocessor space. You can utilize them based on the need. And before purchasing of this component, there will be a lot of varieties. How much hardware is there, how much software is there on the product, we can choose. If we can choose a correct portion, we can reduce power, we can reduce size of the final product, and it can reduce the cost also. So power efficient, smaller scale factor, very cheap. kind of solution if you want to do, you have to do it in a very smart approach. In a design phase, this is a one design. There are multiple blocks. Let's say this block is doing GSM positioning. This block is responsible for Ethernet. This block is responsible for camera. Like that, there are multiple blocks in a system. All the blocks are implemented in hardware, meaning Verilog and FPGA. All the blocks are implemented using C program and on a microprocessor. Simulation, not an actual hardware, simulation. So implement entire thing on hardware, pure hardware. Implement everything entirely on a software, nothing but a microprocessor. And from here we can know each block, how much time it is taking, setup time and hold time, and a cost, power, all the details we can get without hardware in a software, the tool, software tool. Our objective is to find a mutual agreement so that we can implement some of the components in hardware so that they can work very fast, and some of them in software, not so important fast response kind of blocks, something like GPS. Once you know the position, GPS module is no longer needed. Only in the initial state we need. If that is a requirement, GPS can be implemented in software. Let's say camera is very power consuming and it should be operating at all the times. Let's say it should be in a hardware. So that kind of analysis, and we have to find which block to implement in hardware, which block to implement in software. So who will decide the algorithm, genetic algorithm or particle swap? It is easier for a small design, we can do it manually. However, if you go for 1,000 blocks, it gets more complex. Manual approach no longer gives an efficient way, or it cannot be done in a short time. What would be the advantages? Why need to be done hardware software partitioning? It provides you the quality of the design, and time to market would be very fast because there would be number of bugs will be reducing significantly. Lower cost because we are using less hardware and more software, or optimum hardware. It reduces the cost. Reliability will increase, and we can find out early defects. If you use some of them in a software, it's easier to find out. Faster tape out, faster integration is possible. Let's say your block is going to integrate with somebody else. Design time will reduce, better integration and a better performance. The objective is to analyze different optimization techniques and propose a new optimization technique to reduce the time and reduce the cost actually. In a less number of iterations, we have to find out what is the correct combination hardware software in a less iterations. So I will analyze genetic algorithm plus particle swap in a 2 level. I will propose a new one, genetic algorithm with 3 levels of particle swap. First we'll go through about genetic algorithm, a little bit background. Why we use genetic algorithm? It has a feature evaluation. It is very similar to the genes, chromosomes, where there would be an initial population. On the initial population we evaluate based on a cost function, nothing but the selection process. We select the best and then apply the crossover, meaning exchange the chromosomes, exchange the genes within the same chromosome, or can select mutation, meaning instead of exchanging or jumbling within the same chromosome or with different chromosomes. Mutation means completely write a new pattern into the gene. If it is 1010, if you jumble, it can be anything 21 and 20. When it comes to mutation, if there is a 1010, when you mutate, everything will become either 1, all 1, or delete 2 ones so that everything becomes 0. You can do it over all the bits are 1 bit. So the initial population will be selected randomly and the fitness will be calculated over this population. Once the fitness pass, those chromosomes will be selected for either crossover or mutation. The entire thing will be carried using roulette wheel selection, meaning whoever having the maximum fitness, they will be selected. So it's a very easy concept where whoever wins the maximum fitness, they will be get selected for the next level. Look at the flow chart. When we start, we set the genetic algorithm parameters, nothing but the how much population and what is the crossover rate. Yeah, this population, this parameter, and based on that we select initial population randomly and take the population, evaluate the fitness. Fitness function can be less cost and less cost, less power, less faster time response. So those would be the fitness functions. Then we would apply, once we know the fitness, we will be knowing whether it is the best chromosome or not. If not, we would go for the mutation and crossover to generate a new population. Over the new population, if we apply again the fitness function, if it gives the maximum possible value, even after any iteration the value gets same, that would be the best chromosome and we will stop. So who will decide when to crossover or mutate? We take a normalized fitness function over all the population. Then the crossover will be selected randomly based on whoever is having less fitness, they will be get selected for crossover because it is not helping. It is having a low fitness, it has to change, either evolve or die. So those weak chromosomes selected for crossover to make a strong chromosomes. That is about the genetic algorithm. Next one is a particle swap. optimization. It is an evolutionary optimization algorithm traditionally used with bees. For example, there is a bees and it has to cover a lot of flowers for collection of honey or a food. So it is very similar to the traveling sales problem, where a salesman has to cover a lot of cities in a less time, in a less distance. Very similar concept. The bee has to cover a lot of flowers with a short distance. So those kind of scenarios, particle swarm optimization will be very useful, where there will be a current direction of its motion. There would be a local best to this bee, particular bee, and there would be a global best where there would be a fellow bees. At a given time t, there would be a current position and there would be a direction or a velocity vector, and there would be a local best, global best. The global best would be constant and is shared among everybody, every bee. The local best is for only one bee. In this picture you can see one bee has to cover a lot of flowers. There would be two options, whether it can go like this or it can go like this. So it has to cover every flower. So it has to find this optimal path. So the dynamics would be given for every bee, how much velocity or the direction it has to go. There would be a inertial velocity, nothing but a damping function. There would be a local acceleration and a global acceleration. And the next step would be based on the previous step and what is the velocity it has to go, based on these coefficients. The coefficients will vary, will get mutated until it finds an optimal position. Particle swarm optimization. This is a traveling sales algorithm where it has to cover all the cities and with the shortest distance, so that it can achieve in a short time. In the initialization, we select a random number of position and direction, nothing but the velocity, and then evaluate all the fitness functions. Let's say in this scenario we want to find out shortest distance, and the summation should be very small, and we have a lot of patterns. This is optimal path. There would be a lot other patterns. With the initial population of 100, there would be 100 combinations. Each one will have their own distance, and with these 100 distances we can find the local best, and there will be subsequent population. This is one population, there might be another population. The another population will have its own local best. The global best is among different populations, and then it will update the velocity and the position. Then within the same group it will get mutated, or inertia, the damping function and local acceleration coefficient will get a little bit modified so that we don't get the same pattern in the next iteration, there will be a new pattern is possible. Like that, we repeat until the local best and the global best will converge. After that, there is no room for improvement. With that, we go to the genetic algorithm and particle swamp hybrid 2-level. We start with the general population, evaluate each fitness function of one group, and we can select based on the fitness function, calculate the normalized value, and if it is anything falling below normal, then they will go for crossover or mutation. After this, still if there is any low fitness chromosomes, they will get deleted. Let's say top 10 will be selected and they will be given to particle swap. Here, the velocity and the position of the particle will get updated with this fitness function. And they get evaluated over a different fitness function here. Nothing but you can change the damping coefficients, inertial velocity. These values will come from genetic algorithm. Evaluate the fitness. The fitness function is nothing but low cost, faster time, low power, and it will update the local best of one population and the global best over all the populations. It has a particular number of iterations. If it didn't reach that iteration, it will keep repeating the same thing. Once it reaches, it will go back to the genetic algorithm. If it found a valid solution, it will stop, else it will get crossover again. The 3-level approach, the output of the particle swamp will be given to another particle swamp. This is very best useful because particle swamp is very good at the position and velocity related parameters. The proposal is a 4-level hybrid genetic algorithm, particle swamp, particle swamp, particle swamp. The cost function for this is hardware, software, and a power. Hardware is nothing but the hardware cost of the module. Software cost is nothing but the software cost if I implement a particular module in a software. Power consumption, it depends on either hardware or software you choose. Related to that, the power will vary. Whoever gives the less cost, they will be get selected. Here I have run using genetic algorithm and particle swamp, and a 3-level, the 4-level hybrid one. In my observation is that I have taken a 512 particles with a population size of 60 around 100 times. I found out that the combination, the best combination can be calculated within less time, within short number of iterations. Let's say like less than 15 iterations using genetic algorithm, particle swamp, meaning it will reduce the design phase significantly compared to genetic algorithm if somebody uses entirely or GA-PSO. Yeah, with a less number of iterations, we can find out the best approach, hence reducing the time and increasing the efficiency. I have run over simulations. Each simulation, it will try to give the best, however the time will be varying. I have run 10 different simulations and found out the average time is 1 second, 1.049 seconds, and the average iteration is 35 iterations is needed for genetic algorithm. If I cascade with genetic algorithm and particle swamp, the iterations reduced from 34 to 27, number of iterations less. If I add one more PSO, particle swamp, it has reduced from 34, 27 to 25. And final, this is my proposal. If I add one more layer, it will reduce significantly. If you look at the time, it is depending on the number of iterations. Because I am running the simulation on a computer, it is taking a lot of time. If I can implement something on a hardware like FPGA, the time will be reduced and it can find out the best in a less time, less iteration and less time. As of now, it is depending on the hardware where the algorithm is running. That's why you can see the time is more, because we are adding a lot of cascading. It will take time more, however it will do less number of iterations. On a conclusion, I have compared genetic algorithm with combination of particle swarm to give a hybrid level approach. Results show that when you cascade G and PSO over a 3 level, it can achieve better cost function within a less time, less iterations. However, the model requires high computational power. If the implementation can be done on FPGA, we can get the computational time less and we can find out the best combination in less number of iterations. So genetic algorithm particle swamp optimization with a 3 level shows better cost function over the previous generations. If you have something like 1 lakh or more than that combinations like artificial intelligence, then this model will be very useful, reducing the number of iterations. Within a less time, it can find out the best solution. So that concludes my presentation. With hybrid algorithm for hardware software partitioning, especially for embedded design. In embedded design, we have to find out before going to purchase how many blocks have to implement on a hardware, how many blocks have to implement on software, so that we can reduce the cost of the product and increase the better timing and reduce the small factor, space factor. . My simulation shows genetic algorithm with a 3-level PSO can achieve less iteration over the previous generations.